All right. Hello, everyone. Welcome back. So, I don't think there's any logistics updates. We're on week 3. The first test will be in 3 weeks from now, just to keep tabs on all that stuff. Otherwise, I don't think there's any other logistics we need to talk about. So, I've had a few people come to my office hours, which is great. Please come visit me. It's always fun. There's always room. Usually, right now, there's definitely room. As we get closer to the test, the room will only get more and more full. So, and your office hours, just in case. So my office is set up a little differently than most other people's. So my office is a table with a bunch of whiteboards on it. There's snacks, there's tea. The whole point is to have a space where you can actually work on things, and I can help you out. So it's not like me sitting behind a desk and you on the other side of the desk. It's a table with whiteboards, and then a giant whiteboard on the wall. So you can come on in and just work on problems, or you can come in and ask me questions, or anywhere in between. Now, to that end, I've had people come in and working on problems, and so the one that is the most common is setting up the integrals. So I've made a slide here, kind of walking through how to do so. Before I do that, so I made 3 slides that I've kind of added to help out with some things. First is, so there's kind of 2 ways if we have a continuous charge distribution. We have a line of charge, a rod, a sphere, whatever. 2 techniques. Gauss's law and setting up the integral and doing Coulomb's law. You should always try to use Gauss's law if possible. Why? Because it's easier. So if you're like, what do you mean it's easier? Right now it doesn't seem easier. If you'll remember, we did the line of charge with my finger painting. And look, I could do it in like 2 lines. Like it was pretty easy to set up. Whereas when we had to do the integral form and Coulomb's law, it was awful. So, rule of thumb, do Gauss's law if possible. How do you know when you can do Gauss's law? So the rule is when you can draw a Gaussian shape such that either the integral equals 0 or it equals a constant on some part of that shape. And this is true for the following 3 scenarios. An infinite rod or line with a uniform charge density, an infinite plane with a uniform charge density, or a sphere / hollow sphere / a bunch of spheres and hollow spheres together with a uniform charge density, or if the charge density varies with R, there's one problem that has that. That one is beyond what I need you all to do, but it's in there for funsies. Yeah.
Do we always have to do all that work? Can we just jump to the end where it's Q over epsilon 0?
If you happen to know the equation for it, you can jump to the end. The complication comes if I give you a scenario that you don't have the equation for. And the most likely case of one where I'm going to give you a situation where you don't have the equation for is a sphere. So it's very easy for me to give you a problem that basically I have a sphere in the middle surrounded by a shell, which is then surrounded by another shell. And you're like, oh my gosh, that sounds terrible. Gauss's law makes it super easy. If you know how to use Gauss's law. If you don't know how to use Gauss's law, then you're not going to have any clue what to do whatsoever. So this is where you need to know the process, not just have the equations written on your note card for a line of charge and stuff like that, because it will not help you if I give you multiple shells inside of each other. So, how do you use Gauss's law? Here's a nice process for it. Draw a picture with the correct Gaussian shape. The correct Gaussian shape is given on the previous slide. For a line of charge, it's a cylinder on its side. For a plane of charge, it's a cylinder that's upright. For a sphere, it's a sphere. So we have some pictures in previous slides showing those. Next step, solve for E dot dA. Remember, we choose these shapes such that this happens. These 3 are the 3 scenarios that will happen. If it's for a line of charge, that integral will just turn into E times the area of the rounded side. If it's a case of an infinite plane, that E dot dA will turn into E times the area of both sides, the top and the bottom. And then at the sphere, E dot dA will turn into E times the area of the sphere that you drew. These are the 3 possible scenarios. So great. Left side of the equation, done. That's the easy side. The right side, you need to find Q enclosed. And there's basically 2 things to look for here. If you completely if you have all the charge inside of it, then you have all the charge inside of it. You just put capital Q. But if you don't have all the charge inside of it, then you need to find the charge density and then use that charge density to find the charge enclosed. Then set two sides equal to each other and solve for E. So we're going to practice this today. I have an example with the sphere. So this is one of those cases where you can't just have the equation written down because it's very easy for me to give you one that doesn't fit this mold. So you'll see what, if you know the process, you'll be good. If you just have the equation written down, it's not going to work if I just make it one more shell. All right, so this is here. We're going to practice this in just a second. Before I jump to that, I also made a little, let's call it recipe for how to do Coulomb's law. So these are all uploaded, I think, right now. I added this morning. They should be there. They're not there? I literally added them like 30 minutes ago. To week 3. If they're not there, I can upload them I'll upload them by the end of class, but these will be there just if you're like, where do these come from? I'll double check and make sure I uploaded these at the end of class then. All right, before I practice this, and I'm going to show you, this is the one we're going to practice it on. I have a hollow, in this case, sphere, and we're going to practice with that in 3 different regions. Before I do that, the most common question I was getting during office hours is how to set up the integrals for Coulomb's law. And this is something on the quiz that I had for this week. I have a question that is different from the problem sets. In fact, I'll tell you exactly what it is. The problem on the quiz is a finite line of charge, and I say find the electric field at some point directly above the left end. And it has a charge distribution. That's the question. You'll see it when you open the quiz. How do you set up these problems? This is the process. Draw a picture. That's been the process for every single one so far. Draw a picture. Then, write dq in terms of the charge density times dl. And the problems I'm giving you, because you all are currently in Calc 3, I can't ask you to do double or triple integrals. So pretty much any integral I have to do is going to be a 1D integral. So with that in mind, I'm only going to give you situations that are a line of charge. Now that line of charge might be horizontal, it might be vertical, it might be made into a circle, it might be a half a circle, a quarter circle, whatever. It's a line of charge bent in some orientation. So write dq as lambda times dl. Lambda is the charge density for a 1D shape. Then put dl in terms of spatial coordinates that are relevant for your problem. If it's a rod going left and right, you're probably going to use dx because x goes left and right. If you have an infinite rod that goes up and down, then you're going to make it probably dy because it's going up and down. You're integrating over this object. If you have a circular shape, you're going to use that arc length. So you're going to change that dl to r d theta because that gives us the length of a piece of a circular thing. And we did a problem previously with that, so you can look back on that. Great. Once you replace dq with this lambda dl and swapped out dl for appropriate either Cartesian coordinates, dx, dy, dz, or in this case, I guess it'd be cylindrical coordinates. You're then going to break it into x and y. And the way I told you all to break it into x and y is the same way you've been doing it, where if you want you draw an angle on your picture, just like you all break any vector into components, and then if you want the x component, generally the angle you'll draw. Notice I put this as an angle phi. Why did I put it as an angle phi? Because there's a possibility you might have already used theta for a different angle. So we use phi just to be safe, so we don't use the same angle for 2 different things, the same symbol. And we did a problem like this. We did the loop of chart. Well, there's going to be one on there that you're going to have to do this for. And break it into x and y components. Of note, so I told you all, and I'm not going to spoil the surprise, but I told you all in the quiz that the problem is a finite line of charge, and it says find the electric field at some point above the left end. Why am I showing this picture right now? Direction matters. When you all set up the integral, if I say find the x component, and all the x components point to the right, it's going to be positive. If all the x components point to the left, that's going to be negative then. And you need to kind of put, the way I've been teaching you all how to do it, you need to put that negative sign based on the picture. Same thing for the y component. If it all points up, put a positive sign in front of your integral. If your y components all point down, then it should be a negative sign in front of your integral. You're going to see on the quiz that the answers will have pluses and minuses in front of them. So choose the appropriate one. And then you need to get all variables in terms of known variables, based on your picture, based on what's given in the problem, all that kind of jazz. So if you're like, what the heck is going on here? Take this and actually apply it to a problem. And that's how you're going to make sense of this. This is kind of the process. If you have not done one of these problems yet yourself, this is not going to make much sense. If you have done one of these problems, hopefully you're looking at this and like, okay, yes, this is the process I did. As I've mentioned several times, a lot of stuff's not going to make sense till you do it yourself. Especially, or you might think things make sense, and then you realize when you do it yourself that that's not the case. All things ultimately end up with you need to try it yourself. So anyway, there's kind of a recipe to follow. This is the process. This is what I've kind of walked through every student with. This is how you do it. All right. So, try out these things. So back to Gauss's law. So here is the problem that we're going to work on. And there's a few kind of variations of this. There's a problem set. Says a total charge Q is distributed uniformly throughout a spherical shell with inner and outer radius R1 and R2 respectively. Find the electric field at distance R, and there's three different places that we're looking at. One is inside the inner radius, one is between the inner and outer radius, and the last one is outside the outer radius. And there's all the answers there. I'm actually going to delete them. You can see one of them is worse than the others. And it looks bad, but if you just go through the process, if we follow that step process I showed you in the previous slide, that's going to help us out. So, one at a time. We're going to do each one. So we pick a random spot inside it. It doesn't say where. It doesn't matter where, as long as you're inside it. That's our first point that we're going to consider. That's, let's just call it point A, because it's for part A. So, if I want to find, go ahead.
You should pick inside only because it's part A, right?
Part A says inside. Yep, part B will be at a different spot. Part C will be at a different spot. So part A will be here, part B will be here, part C will be here. Notice it didn't matter. As long as I was following those rules, it doesn't matter where, because there's symmetry. If I'd spun the thing, it would look identical to you and you would never know the difference. So, step-by-step process. Draw a picture with the correct Gaussian shape. Now, in this case, it's a sphere. So the appropriate shape is going to be a sphere. Now, I'm not going to actually draw a three-dimensional sphere. I'm just going to draw like a slice of it, but you need to know that that's a sphere. If you want, you can try to get fancy and try to draw a sphere, but whatever. Don't worry too much about that. It's a sphere. You need to know it's a sphere. All right. So, next step. So let's write actually Gauss's law. Once you see this problem, you kind of have to immediately realize we're going to do Gauss's law. So, remember I told you all the problem-solving process. Draw a picture. What am I solving for? What processes, what do I have? And then, what processes can let me solve this? So kind of going through those steps. Picture is there. What am I solving for? The electric field. What do I have? I have a bunch of radiuses. How am I going to solve this? Your mind immediately needs to go, this is a Gauss's law problem. You have to recognize that if you have a sphere or shells, it's Gauss's law. That's just something your brain has to say, this is the only way to do that I've taught you. To solve this using an integral with Coulomb's law, you would have to have a computer. Because the electric, it'd be awful. You could think through how you would do it, and it would be unpleasant. Doing it by hand would be almost impossible. All right, Gauss's law, it's possible. Yay! So, Gauss's law says integral of E dot dA equals Q enclosed over epsilon naught. When solving Gauss's law, we start with one side at a time. I tend to start with the left side because it's on the left. Whatever, it doesn't really matter what side you start on, you gotta do them both. E dot dA is the electric field times the area. So in this case with the sphere, we do the area of the sphere. I mentioned that in the previous slide, and we chatted about that last class. So in this case, this left side is going to turn into E times the area of a sphere, which is just going to be E times the area of a sphere is 4 pi r squared. The r here is the radius of the sphere that I drew. So in this case, it says find distance r when I'm inside of it. So my distance r, it's that sphere. It's the sphere that I drew. It's the sphere, this E dot dA is over my Gaussian surface. Left side done. Easy. Left side's generally the super easy side. Now we're going to do the right side. Q enclosed over epsilon naught. I'm going to let you all think about that. So remember, there was 2 steps for finding this. The first was, if you just know if the charge is, if you know how much charge is enclosed, put how much charge is enclosed. If you can look at the picture and figure it out, great. If you can't, you're going to need to find the charge density inside of it and go from there. So think about it for a second. See if y'all can figure out the charge enclosed in this. Figure out whether or not you're going to need to find the charge density and all that.
Why is the area 4 pi r squared?
Yeah, that's a great question. It's the area of a sphere. So if you have a bubble, like a bubble, the area of a bubble is 4 pi r squared.
Oh, the surface.
Yeah, the surface area is a great, that's a better way of clarifying that. It's a surface area of a sphere. Surface area of a sphere. These slides will 100% be on Canvas. Yeah, I made the updates today. I thought I'd uploaded them. It looks like I hadn't. While you all are thinking through this, you know what? I'll just kind of chuck them there with the 3 guides. It's quick enough for me to do. Yeah, these are the ones I uploaded. They should have it. No, they're not there. That's very sad. I put the wrong ones. All right. All right, ostensibly these should be correct now. All right, so y'all tell me, how much charge is enclosed by this thing?
We don't know.
You do know. Where's all my charge in this picture? It's on the gray thing. Where's all my charge? My charge is distributed on this gray surface. So how much is in my little bubble I drew here? 0. There you go. What's the electric field inside this? 0. Yeah.
Sorry, this is a dumb question. Why is the charge only in the gray?
It's a good question. It's in the problem. It says a total charge Q is distributed uniformly through a spherical shell. So in this case, my object is a spherical shell, so a sphere with the inside hollowed out. Okay. And the inside is hollow, meaning there's nothing there, meaning there's no charge there. Yep, so if we do this side, my charge enclosed is 0. So then I just set these two equal to each other. Therefore, electric field inside is 0. There you go. The power of Gauss's law. It's super handy. It lets you sign stuff that if you had to do this with Coulomb's law, would have been an absolute nightmare. Now, if you're like, how is it 0? It's because for every electric field, for every charge on this side, there's one on the other side, and so the fields kind of cancel each other out. You're like, but these are closer. That's true, but when you break them into components and all that, it would end up working. But it'd be messy to show you that with Coulomb's law, if not like almost borderline impossible. 0 divided by anything is 0. Yep, so if you set these two sides equal to each other, 0 divided by 4 pi r squared is 0. Yep. All right, that's the easy one.
Well, wait. Like, you asked for the inner radius, and you asked if there's any charges there, right?
So there's charges in here. We're going to do that one next. Right now, we're doing point A, which is inside it. And inside this, there is no charge. There is no charge in that red bubble I just drew on there.
So no charge equals 0?
If there's no charge enclosed. Enclosed means how much charge is inside my bubble I drew. All right. I'm going to jump to part C, because part C is going to be the easy one. And then I'm going to come back to part B. So part C is going to be, I'm going to take this picture, I'm going to steal it, there it is. So part C says find the electric field at some point outside of it. So at some point out here, find the electric field. We do the same thing. We draw a Gaussian surface. In this case, it's a sphere. This whole object is a sphere. We're surrounding it with a sphere. It's very hard to draw spheres, especially hollow ones. So we do the exact same process. E dot dA equals Q enclosed over epsilon naught. We then solve for the left side. It's a sphere. The area of a sphere is still 4 pi r squared. You're going to start to see some, like, the left side's always pretty straightforward. Yeah? We are assuming this isn't a, it wouldn't matter. Okay, well, the only thing it would change, if it wasn't in a vacuum, this epsilon naught would change. But yeah, it's a good question. You can very much assume most of these are in vacuum, but it honestly doesn't change much of anything. As nice as this, yeah. Epsilon naught is actually basically the same if you're in air as well. So, all right, so left side, easy, done. The right side, same thing. Think about it for a few moments. How much charge is enclosed? I'll even put the word problem up here as well, because you might need that. Boom, put that up here. It's totally going to fit. Great. Yep, so good. I'll move everything down slightly. We don't need that much space for this problem. In the magic of technology, space is free. All right, so how much charge is inside my red bubble here?
All of it.
All of it. What's the symbol for all the charge?
Q, E, and C.
It's just Q. How much charge is inside of it? Q. So on this side, how much charge is enclosed now? Q. That still is over epsilon naught. Don't lose your epsilon naught. It still exists. Great. These two sides equal each other. Solve.
How is there all of it?
Because it's all inside this red bubble.
That you randomly make up.
We make this sphere around it, and we figure out how much charge is inside that sphere. Yeah, that's the trick. We draw the shape, and we figure out how much is in it. Yeah.
What if you had randomly drawn the bubble not to? Will that be wrong? Does the bubble have to touch the point that you're trying to work?
Yes, the bubble has to touch the point we care about because this E is the electric field on that surface. Yes. The bubble has to touch the thing you care about because that's how we're finding the electric field on that surface of the object. That's the math trick.
Then, like, what if it's so small and like it doesn't touch it? You can make it so small.
You draw the sphere such that it touches that. Wherever your point C is, draw a sphere with that radius. When it was smaller, you made a sphere that was smaller. When the point was
if it was like a 2D, like the plate where you draw a cylinder, that.
Yeah, it's a great question. If this was a cross-section of a wire, imagine instead this is a hollow wire. You wouldn't draw a sphere around it. If this was, and that's actually good foreshadowing of the quiz problem I gave y'all. On the quiz upcoming, the picture looks very similar, but it's not a sphere. So you don't draw a sphere around a line of charge. You draw a cylinder around a line of charge. And the area of a cylinder is not 4 pi r squared. Be careful based on what the problem is doing. You need to draw the right shape for the right object. Yeah. Oh, yeah. So let's write this out. We're going to see something wonderful. Divide the 4 pi r squared over 4 pi r squared epsilon naught. And he raised a good point. If I just write this like this, Q over 4 pi, Q over r squared times 1 over 4 pi epsilon naught. Oh my gosh, it's just Coulomb's law. Turns out this hollow sphere just looks like a point charge when you're outside it, which is kind of cool. And that would be true even if this had a non-uniform charge density, it wouldn't matter, all that kind of jazz. So this is one of those things when you get outside of objects, they sometimes simplify to something easier. It's a nice little thing. This is actually, you can use Gauss's law to prove Coulomb's law. They go back and forth.
That's a valid answer.
Okay, Q over R squared is the answer. Yep, they're the exact same thing.
K is 1 over 4 pi.
K is 1 over 4 pi epsilon naught. Yep. All right, now let's do the unpleasant one after I answer this question.
So it doesn't matter that the inner radius doesn't contain any, like you wouldn't have to subtract radiuses.
Not yet. We don't care because all we care about is the charge enclosed. and we've enclosed all the charge. And this problem, it says the total charge is Q, so that's the total charge. Yep, that's a great question. It's just not distributed through the middle. Now, let's do the next one, and this one I'm going to kind of work through maybe a little quicker for the sake of, well, not a little quicker, but I'm not going to give as much time. I'm going to kind of do it with you, well, in front of you all. So now this one is find the electric field at some point in between the two. We're in between the two now. Find the electric field at this point that is somewhere in between the two. We do the same thing. We draw our sphere because this object is a sphere. Now, here's the challenge. This is in between the two situations. When we were inside, we had nothing. When we were outside, we had all of it. We are somewhere in between. We do not have nothing, and we do not have all of it. We have somewhere in between. And this is where I told you all the trick in the slide up here. If the charge is completely enclosed, or like you can just kind of look at the picture and figure it out, awesome, do that. That's what we did for part A and part C. If not, if a partial amount of charge is enclosed, not the entire object or objects, but some partial amount, find the charge density, and then use that to find the charge enclosed. So I'm going to walk through this process with you to show you the magic sauce. So, our goal is we're trying to figure out how much charge is enclosed by this bubble. Now, the only place there's charge is this part that I'm kind of highlighting here in red. Yes, the sphere does the whole thing, but the middle is empty. So we're trying to find how much charge is on this kind of smaller sphere, hollow sphere. That's the goal. So how are we going to do this? The same exact way we've been doing the problems. We start with E dot dA equals Q enclosed over epsilon naught. We start with the left side. Left side still super easy. It's just E times 4 pi r squared. Why? Because it's a sphere. The surface area of the sphere is still 4 pi r squared. If this was a line of charge, it would not be 4 pi r squared. So, keep that in mind. Great, left side done, easy. This is the tricky side. Q enclosed is not a trivial thing. I can't say it's Q. I can't say it's 0. I can't just say it's half of Q. It is a function of where I'm located. It's a function of R, among other things. So follow the process I just told you all. We're going to use the process I just mentioned.
Why would R be R2 minus R1? So it was just
R2 minus R1 would give you the thickness of this. This R is an arbitrary distance that I picked.
Okay.
I could be super close to the outer edge or super close to the inner edge or anywhere in between. So we're solving for anywhere in between. So we're getting an infinite number of solutions, which is kind of nice. Lets us solve it. If I gave you an R, you'd plug it in and it'd be done. This is the benefit of working in variables. So, remember, I told you all, we need to find the charge density. If you don't know why yet, just trust the process. This is the process for doing this. If we can find how the charge is distributed in space, so let's just remember the definition of charge density. It's Q over V. Three-dimensional charge density is charge over volume. Okay, how is this useful? If I know the charge density, I can just multiply it by the volume of this red squiggly thing, and that's going to give me the charge enclosed. The charge density is uniform. So if I find the charge density for the total Q and the total volume, I can then plug that back in to find the charge enclosed if I know the volume enclosed, which I definitely can figure out. So that's the strat. We can find an equation we know Q. We know Q total. It's given in the problem. It's just Q. We can find the volume of a hollow sphere. It's quite easy to do if you know the equation for the volume of a normal sphere. And then we can take this, plug it in right there. We can write an expression for the volume enclosed, and then solve for Q enclosed. So let's try it out. Let's go through the process. It's a fun time. These ones are fun because they're puzzles. You'll see when you do them. Trust me, they're fun. All right, so Q total is just Q. Shock and all. Total Q is Q. That's what it says in the problem. The volume total. Here's how to do this. The volume of a sphere is 4/3 pi r cubed. Why is the volume of a sphere 4/3 pi r cubed? You're going to learn in Calc 3 when you do a triple integral over a sphere. If you haven't done it yet, you'll do it at some point and you'll derive the expression for it. Yeah. It's good for you. Yeah. If you don't know where that expression came from, at some point in your life it was probably told to you. By finally reaching Calc 3, you can actually derive it yourself. You'll get there. Great. 4/3 pi r cubed. That's the volume of a solid sphere. All this sphere is a solid sphere with a smaller sphere inside it hollowed out, i.e. subtracted from it.
So it's a donut.
It's not a donut, because a donut would be a toroid. This is a sphere with a smaller sphere cut out of it. So, let's kind of talk that through. So we have a sphere, a solid sphere, with radius R2, and then we subtract out the smaller sphere with radius R1. Ta-da! We've derived the expression for the volume of a hollow sphere. It's just a lot. Take a solid sphere and subtract out a smaller sphere.
That's why you have the two radii.
You need both radii, so you can factor that out, and you get 4/3 pi R2 cubed minus R1 cubed. Ta-da! You can look this equation up if you want somewhere online, but this is how you would derive, quote-unquote, the expression for a hollow sphere. It's pretty straightforward. It's just coming from, I just subtract out the middle. Awesome! So what? Put that here. Now we're going to take that charge density. We know Q, we know R2, we know R1. Those are all known variables. We can now take that and plug it into this one down here, where this actually finds the volume, the charge enclosed. So, take this, move it over to the side, because I'm going to need more space. So we're going to take this row and put it right here. So that's going to turn into the following. We're going to have Q over 4/3 pi R2 cubed minus R1 cubed equals Q enclosed over volume enclosed. Volume enclosed is the exact same process we use to find volume total. The volume enclosed is just this sphere here, this part highlighted in red. It's a cylindrical, it's a hollow sphere that's smaller than the original sphere. Yeah. Yep. That's exactly it. Yeah, so if you hear what he said we're just going to change out R2 for R. We are finding the volume of this thing I am highlighting in red right now, i.e. a hollow sphere that's smaller than the big sphere. What is the volume of this sphere? Again, I'm going to give myself a little bit of space. I don't want to stick it all in at once and just confuse too many people. The volume enclosed is going to be 4/3 pi R cubed minus R1 cubed. It's the exact same process to find the volume of the total. Just replace R2 with R. My outer radius, quote unquote, of the smaller sphere is R. Great, chuck that in here. 4/3 pi R cubed minus R1 cubed. Magical things happen. We don't have to deal with the pi's or the 4/3. Rearrange this equation to solve for Q enclosed. I'm going to take this to the next slide. Kind of cram things in there a little bit. Well, actually, I don't think I need to make it to the next slide. To the power of shrinking things, I have more room. Wow.
Are you missing the 2 subscript or the R?
No, it's because it's the outer, we're finding the volume enclosed, and the outer radius of this is R. Yep. So, Q enclosed, therefore, just equals Q times R cubed minus R1 cubed divided by R2 cubed minus R1 cubed. And finally, we can take this and set it equal to this over epsilon naught. That's last time. Oh, it's basically done though. This is the easy part. So therefore, E times 4 pi r squared equals Q over epsilon naught times R cubed minus R1 cubed over R2 cubed minus R1 cubed. And if you solve for E, we get Q over 4 pi r squared epsilon naught times this ratio. This ratio is literally just how much volume is enclosed out of the total. It's a ratio of volumes. Yeah, so this is a good exercise.
Did you sub in J again?
You could, if you wanted to. You totally could. But this is the answer. We know R. It is now written in terms of variables I know, and that's the end goal. So yeah, what problem might I give you all on a quiz? Like if I gave you all something like this, it'd be a free response, and it would very likely be some like spheres inside of spheres kind of thing, or lines inside of lines. Fun fact, a coaxial cable is just one wire within an outer wire around it. So coaxial cable is just a wire inside another wire. And you can find the electric field inside it if it was like a static situation. Yeah.
You can't factor out the Q, like raise that whole thing over counter, right?
No, you can't. No, you can't factor it out. Yep.
And then if this was like a 2D or 1D, instead of it being rho, it would be like lambda or...
Yeah, if this was 2D, that's a great question. If this is 2D and this is a wire, you would instead do sigma equals Q over area. The charge would be distributed over an area. Well, and then an area times the length if you actually enclose it. No, because it's a cylinder, so it would actually still be volume. It'd be the volume of a cylinder. Yeah.
Wait, for the volume total, it's like R subscript 2 minus R subscript 1.
Yep.
Do you think you could explain like conceptually like how it connects to the circle for the sphere?
From this, it's a solid sphere minus a smaller sphere. Take the volume of a solid sphere, subtract the volume of a smaller sphere inside it, boom, you got the equation for the volume of a hollow sphere. Yeah, that's one. You can kind of look into that more if you want. There's probably some nice animations online that kind of show it more. This is ultimately the equation for the volume of a hollow sphere. That's all I derived. Yeah. All right. For the sake of time, I'm going to go ahead and jump into, I want to start talking about electric potential energy. Gauss's law is a math trick. At the end of the day, Gauss's law is a math trick. You may be like, why are we learning it then? Because it's useful. You all in your engineering classes are going to learn a lot of math tricks that are based upon the physical rules and other equations. But these tricks, a good engineer is clever. A good engineer is clever and finds workarounds that make the life easier. And so if you don't know what I mean, you'll see what I mean one day when you look at mechanisms. So for example, when you design a product, you want to design a product with as least moving parts and as few things as possible. You got to be clever. This is basically a clever way of setting up a problem that we wouldn't otherwise be able to solve. Humanity is not accomplishing things purely by brute force. It's by doing clever things that make our life easier. We're not pushing boxes on ground. We're putting the boxes on wheels. We're doing things that make our life easier. This is one of those things.
Are you going to do that problem that you skipped the other day to a finger problem?
I won't, but I'll upload the completed one. And actually the slide for it's completed. Oh, this one? I'll,
No, I think it was number 5. That guy.
This one? This one is very similar to that one. So this one I don't plan on solving out. But it's just like it, except this is that whole, it's a line of charge instead of a sphere. All right, so great. There's that. Practices, y'all. Like anything in life, it's going to be hard at first, but then once you practice it enough, it'll get easier. If you don't practice it, yeah, it's not going to make any sense. Gauss's law is kind of funky because it's not like I'm not like necessarily teaching you physics. I'm teaching you how to apply the physics to solve problems you otherwise couldn't solve.
When you say like line charge, do you use the area of a sensor?
Yes. Yeah, if you're doing a line of charge, you would do the area. You would do the volume of a cylinder if you wanted to find the charge enclosed. If you did a line of charge, you'd have a cylinder along the length of it. The charge enclosed would be the charge enclosed by a cylinder. So the volume of a cylinder instead of volume of a sphere. Yep. All right. Now, getting into some more like actual physics stuff. Gauss's law is one of these situations where it's a math trick, and there's going to be another case where we're going to use flux in the future. It's going to be super nice about Ampere's law, but that's a future problem. Electric potential. So, this is something that you have heard about, and you might not realize it. And you're going to realize you've heard about it once I tell you the symbol for it. The symbol for electric potential is V. It's voltage. In this class, we are going to call it electric potential. but another name for it is voltage. And what does it have the potential to do? It has the potential to have energy. This is not energy. Electric potential is not energy. We're going to start with energy, and then we're going to derive electric potential from it. Which you're like, oh my gosh, that sounds terrible. It's going to be really simple. So again, this is kind of a new thing. This is a new way of looking at things, and this is motivated by something you did in Physics 1. Physics 1, you all started, you had to do a bunch of vectors and stuff. And you're like, man, this is a lot of math. And then at some point, you probably learned something magical called conservation of energy. And conservation of energy is great because it's all scalars. Electric potential is the same thing. We're going to use electric potential because it's kind of a way to find energy, and energy is awesome. When you all look at a battery, it doesn't tell you the electric field it outputs. It tells you the difference in potential between the two sides. Because this is super handy and it lets us avoid a lot of math. Electric fields are still incredibly useful and incredibly important. But for a lot of macroscopic things, we can use voltage. And I'm going to make some analogies and connections to things you already understand to explain why it's useful and all that jazz. So, we're going to first derive electric potential and electric potential energy from forces and fields. We're going to talk about what they are, and then we're going to talk about how they can be used, which is something you already know. You already know how electric potential can hopefully be used. You already know how voltage can be used. So this is incredibly useful and incredibly relevant because every single one of you has an electronic device somewhere on their person right now that's using voltage. Yeah, your heart does also have a potential difference. It uses it's used to make current, electricity, all that good stuff. All right, so let's see if background knowledge. Remember, all learning is connecting old knowledge. How long do I want to spend on this? I'm going to give you all this, I'll give you all 2 minutes. Let's see how that goes. These ones are uploaded. Fingers crossed. Oh, okay. Through the power of picking the right ones. My apologies. I made some updates to them today and I must have copied the wrong ones. Let me know if those are pretty. They're the ones I just opened now. Yeah, apologies for that. There were some updates I made and I must have overwritten. Yeah. All right. You drop a water balloon with mass 1 kilogram from the top of the physical science building. Open a splash someone. What value is the closest when the balloon hits the ground? Again, I'll give you all till 2 minutes. There's a couple ways you can solve this. One is easier than the other. I guess they're both. Well, one is definitely easier.
Oh, wait. Yeah.
All right, 20 more seconds. I know this is probably not as much time as you need, but it's more to remember how to do it and then see if you can get close. All right, plus 7, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. So there's 2 ways to solve this. I'm going to emphasize one way because it's the mindset I want to get you all in. This is conservation of energy. Conservation of energy says energy I start with plus the work done equals energy I end with. What energy do I start with? I start with potential, and I'm actually going to write this in the variables that we're going to use in this class. I have no kinetic energy to begin with. There is no work done. We're going to assume that the work due to friction is 0. We're going to ignore air resistance because otherwise it's awful. And then it's going to have no gravitational potential if you're clever. If you set the height at the ground to 0, then at the bottom you have 0 potential energy. You could have set it to whatever you want. That's going to be something I'm going to chat about. The ground does not have to be 0. It could be 10, as long as then if you made the ground 10, then the top of the building would be 20. We're going to chat about that. That's relevant. Kinetic energy final. Awesome. So we get mgh. In fact, I'm going to write this a different way that I like to use. mgy equals 1/2 mv squared. M's cancel. The velocity equals the square root of 2 gy. And that's it. Which I'm fairly confident is 14. I will plug it in just to be sure. The only reason I'm thinking it's 14 is I put 196 on there. All right, great. I'm going to trust y'all. 14. Yay, great. You all remember conservation, or you might have done kinematics. That's fine as well. I want to emphasize energy. Why is energy useful? If instead this thing had like rolled down a hill and we ignored the energy due to rotation, one of the cool things with energy is we don't care about the path it takes. So if this thing had instead rolled down a hill and we ignored the rotational energy, or we said it was so small, the path wouldn't matter. This is a super... Conservation energy explains everything in the universe. Everything in the universe wants to get to lower energy. That is a rule of thumb that explains everything in the universe. And so we're going to use that when it comes to electrons and things like that. So, all right, another quick refresher. From Physics 2048, what quantity is determined by taking the dot product of force and displacement? Is it the spring constant, displacement, acceleration, or work? I'm going to give you all 40 seconds. Either you know it or you don't. If you don't, I'll remind you. All right, we're supposed to start at 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. So, the answer is work. That was a definition in physics. Work equals the integral of F dot dl. What does work do? It increases the energy of your system. If you apply work, if you apply a force in the direction you're moving, that object will get faster. If you apply force in the opposite direction you're moving, you will make it go slower. You're either adding or taking away energy. Positive work, add energy. Negative work, take away energy. That's what work is. Well, we've learned about a force in this class. A new force. The electric force. So yeah, this is just a nice little written thing of that. So a couple things to remember. Work is an integral of F dot dr or dl or dx or whatever coordinate you might want to use. Work is also the negative change in potential. That comes from the derivation with like, if you find the work done by something falling, you realize it's you get this negative sign. Something you can kind of look up. This is something I showed in Physics 1. If you're like, well, how's that true? Feel free to look that up. I won't spend any time on it now. Just because we don't have the time. But these are both true statements from Physics 1. All right. So, we learned about a force. We learned about the electric force, and we learned about it in terms of the electric field. So, if you're like, whoa, where did this come from? Remember, y'all, that E equals F over Q? Through the magic of algebra, F equals E times Q. We then can just plug that in here. So, if you're like, whoa, what happened here? I'm going to kind of write this out. In fact, I'll do it on the other slide. And then I'll show the one with all its prettiness. So, reminder to y'all. F equals, in fact, let's write it this way. E equals F over Q. Therefore, F equals E times Q. If this equals work and this equals work, guess what? They equal each other. If A equals B and B equals C, then A equals C. Yeah. So we're going to use this because we're going to find the electric potential energy due to two charges. There will be based on how much my potential energy changes. Yep. So we have to do it based on this is the definition, and we're going to use it. Yeah. Yep. It's not guaranteed those charges will move. Yeah. It's not a guarantee that we're going to let those charges go. So if these two things equal each other, then they equal each other. So negative change in potential equals the integral of f dot dr. Through the magic of substitution, we take this and we put it here. And so it turns out that the negative change in potential equals the integral of EQ, E is a vector, dot dr. And that's what the next slide shows.
You factor out the Q.
You can totally factor out the Q, it's a constant. And that's what happens here. And we also move the negative to the other side because we like to get the left side by itself. So if you're like, what happened? We just made this swap. It was on the last slide. We pulled out the Q. We moved the negative to the other side. And ta-da! We have discovered how much the energy of we can find the energy, how much the energy changes based on how charges kind of move around and where they're located, really. If you have two charges, you can find the energy stored in that system. Why is that useful? If you can find the energy stored in that system, you can determine what would happen after. Just like we did with the water balloon dropping. If you all could find how much energy was stored in that water balloon by being 10 meters high, you could figure out how fast it's going to go when it gets near the ground. And you can figure out which direction it's going to move. Why? Because it's lower energy at the ground. So, things are going to move to lower energy. So we can find the energy stored, we can determine which way they're going to move, and we can figure out how fast they'll move and all that kind of jazz as well. Super, super useful. Yeah? The bounds of the integrals are, so this dr is kind of over a path that this electric field is being applied to. So if you want to find the energy stored, so here's something kind of funky, is we have to kind of pretend like we're moving that charge from one location to another. So we're going to move from one location to another, and I'm going to give you all a specific example of this to see this. We only store energy by getting something somewhere. So like, how do you get a balloon? How do you have a balloon gain energy? How do you have its potential energy change? Look, if I leave this umbrella here on this desk, it's never going to gain more potential energy. It's never going to happen. So what do I need to do to it? I need to move it. If I move it from some initial position to some final position that's higher, I've caused it to gain energy. I've caused its energy to change. I've now stored energy in it. So that's a great question. These bounds are where I start, where I end, and we're going to apply them to a couple of situations. A lot of this is just derivation in the beginning to help you understand where it all comes from. And then we'll start to kind of get to the parts that are super useful. So, great question. Here's one of those examples. 2-point charges with charges Q1 and Q2 are initially on the x-axis. One's at the origin and one's at xi, respectively. That's where it starts. How much work must be done to move the charge Q2 from x1 to a new position xf? How much energy have I either added or taken away from the system, depending on what type of charge we might have and all that jazz? So we draw a pretty picture. One charge is here. Q1 is going to be here. And Q2 is going to be located wherever I want it to be, but let's make it nice and simple. Let's just put it over here. We're going to say that's where it starts. This is my xi. What direction do I want to move it? It's arbitrary. It doesn't say here, so just pick a direction. I'm going to pick to the right. I'm going to then say it's going to move to some position over here. Cool. Then we write our equation. So the work done, and again, you can kind of write this either way. So work is the negative change of potential energy equals Q times E dot D, now I use ds, dr. What direction is my charge moving in this picture? Up, down, left, right, or like radially?
Right.
What variable do we like to use for? Yeah, so we're going to use x, because that's the direction it's moving. We're going to pick the variable that makes sense, the direction it's kind of going. Cool. Now, this is the charge. Q2 is the one experiencing the field. E1 is the electric field made by the other charge. One charge makes a field, the other experiences a field. Remember, that's always a thing. Cool. And our bounds are xi to xf. Now we just do a substitution. We say, what is the electric field due to a point charge? And it's KQ over R squared. Now, something I'm going to do right now is I'm going to get rid of the dot product. The direction of the electric field is going to be parallel to the direction that it's moving. So this charge is going to make an electric field pointed to the right. So if I wanted to, I'm going to remind you all, I'll kind of chuck it up here. E dot dx is equivalent to the magnitude of E times the magnitude of dx times cosine of the angle between them. If they're parallel, it's 0. Long story short, when y'all are doing these, we're never going to have to worry about the dot product. Okay? In this class, we're not really going to have to worry about it. But if you're like, where did it go? Another thing I'm going to also point out, well, I'll put it like this for now, and then I'll just straight up tell you, we can change that R to X. Because if you draw on the picture, this is R, which is the exact same thing as X. They're the same thing in this picture. So I can just swap them. Okay, Q over X squared dx. All right, and I have the utmost confidence in your ability to do this integral. Try it out.
What about the negative?
So the negative, I chucked it over here. It's next to the... So work is defined as the negative potential, which means it equals the positive integral. Yeah.
Why did you substitute in Q or Q?
If I'm going to integrate over dx, I need to get R in terms of x.
No, you're like from EI to that.
The electric field due to a point charge is KQ over R squared. Yep.
If plus Q, then you just get X negative. But if you can't pull that out.
So it's an integral. You can pull out your constants. K is a constant. Q is a constant. Q is just how much charge. That is not changing. My charge is not changing how much charge it has. So long story short, we can pull out the K. We can pull out the Q. So it's the integral of 1 over x squared dx from xi to xf equals Q2 times Q. And I lost a Q somewhere. Yeah, Q1, Q2, Q1 with a K in front of it. Times negative 1 over x final plus 1 over x initial. The integral of 1 over x squared is negative 1 over x, so you get a negative sign. And so this, you can write it here. It's prettier. I don't know if that's prettier. That's the answer. How much work did I do? 1 over xf plus 1 over xi, and you're like, this is kind of funky. Does this mean I did negative work? xf is bigger than xi, so this is going to be a smaller number. This will be a bigger number. So the field will have done positive work. It will have added energy to the system. How do we know that? If I assume these, look, I drew a direction of the electric field. If I assume these are both positive, this is going to push it and make it go faster. It gained energy. So they all kind of connect together.
What about the negative from the other side?
So this is the work done.
Oh, okay.
Yeah, this is the work done. And in this case, if you plugged in numbers, xf is bigger than xi, so you get a positive number.
So you can always just skip that U thing.
Yeah, and a lot of this is just deriving. A lot of this is just showing that things are connected. So don't stress this too much. We're going to apply this to a situation where I will say it's like more important. A lot of this is just deriving the energy stored with two charges. Yeah.
Review slide. Why is there two Q2s?
Because I typo. Great question. Thanks for catching that. Q1, Q2. One makes the field, one experiences the field. All right. So,
Can you go back here?
yeah.
Is that Q1 on the numerator there?
Yeah. This one's Q1.
Oh,
Yep. All right, so all of this is building to get to the point where we're going to find the energy stored between two charges. That's the end goal of this. Here I picked arbitrary distances. I picked random distances. But here's the logic. Here's the logic we're going to use. And let's see, it's in this next one, but I want to kind of derive it. I got a charge. Boom, here's a charge. If I want to find the energy stored in a system of two charges, I need to do this integral. If I want to find how much energy I have in a system of two charges, I'm going to do this integral. The one we just did, the one we just solved. Now, here's what's going to be different though. So we did this integral, awesome. If we write this integral, so I'm going to go ahead and steal this solution here. Boom, put this over here. So I'm going to steal this and put it over here and then erase the W. These two things are equal. We just solved this. My x final is going to be where it ends up. If I just want one term of this, I want the energy stored. Where should I put my charge such that this initial term disappears? Where should I place it so that I can make this initial term disappear? I know my final position is going to be right next to it. I'm trying to find the energy stored in two charges, so I need to bring this charge from somewhere and put it a distance, xf, away from it. So if we put the origin, what would be the value of xi then? 0. 1 divided by 0 is infinite. That's not going to work for us. But that's a good idea. What's another idea?
Same thing as XF.
If you do the same thing as xf, they'll cancel out and you have no energy.
Oh.
Yep.
Reflected across the y-axis?
If you do it reflected across the y-axis, then you'll just get, I think, a -2 term. You'll get an extra 2. I want to make this term go to 0. Just the 1 over xi. If you make it infinitely far away, if I bring this charge from infinitely far away, I can find how much energy is stored. Because that's basically the idea. If I bring this thing from infinitely far away to this point, that's how much energy is stored in it. That's how much energy will be stored in the system, as if I brought this thing from infinitely far away. If I wanted to release all this energy, I would need to let the second charge move infinitely away as well. That's the thought process. So, if I set this equal to infinity, if I set it starting at infinity and I bring it to some distance, xf, what happens to this whole integral? I get k, q1, q2, times negative 1 over xf. What happens to my negatives? They cancel. So what is the energy stored between two charges? It is just k, q1, q2 over, I'm going to say the distance between them. This is the energy stored in two charges. You take a charge, you place it somewhere. It's free, it's easy. There's nothing repelling one charge by itself. If you want to bring another charge in, it has to fight, that other charge is fighting it. And you store energy by bringing it. So, this is the derivation. All this work was just to show you this. The energy stored between two charges is k, q1, q2 over r squared. Remember, everything I'm trying to teach you on this class is from observations of reality up. We don't skip any steps as far as where things come from. Everything is built on something we learned beforehand. Unless it's an observation of reality. All right. I'm actually going to kind of remove it. This one's kind of funky. If there wasn't one charge in an external field, you would do this. All right, and this is the ability for the system to do work. What does that mean? If I release these charges, stuff's going to happen. They're not going to stay there. I've stored energy in this system. If I've stored energy, it can now do work. Work meaning it can apply force. There's forces that can be applied and energy can be released. Changed to other forms. All right. So, cool. Energy stored between two charges. So let's just, play around with this equation a bit. If I have two charges, both positive, what happens to the energy stored in this system, the total energy in the system, if I double the distance between them? Does the energy now double, half, stay the same, or quarter? Basically, what happens to my ability to do work? Am I able to do twice as much work with the energy stored in this? Half as much work? Same amount of work? Yeah. Was it square in the last slide? I really hope it wasn't. Okay. But that's important. Yeah. All right, give y'all about 10 more seconds. And 5, 4, 3, 2, 1, 0. So remember, way back, I showed you all the trick for doing these types of problems. If I change this, how does this change? So we write the original. Here's the energy stored between two charges, K, Q1, Q2, over R, not R squared. If you made it R squared, you made it the electric field. Or no, you made it a force between the two charges. If you put a squared, you found the force between them, not the energy stored. That integral removed that squared. Now, great. How do we do these problems then? What is my new energy stored? K is the same. Q1 is the same. Q2 is the same. My distance doubled. So you just pull out that doubled. It's on the bottom. Keep it on the bottom. And boom, there you go. My energy is half the original. And this makes sense. Let's think about, does this make sense? If they're farther away, they're not pushing on each other or pulling on each other as much. I don't have as much energy stored in it. If I release them, they're not going to release, quote unquote, as much energy. Physicists love energy, and so should you. And here's why. Our entire society is built around changing energy from one type to another. Your whole existence is changing energy from one type to another. What do you do day to day? You eat food. What does that food do? You consume it, and it changes to heat and motion and things like that. What do you do with that energy? You make other things move. You take energy and you transfer it. The entire electrical grid exists to transfer energy from one location to another. That is all electric. All those cables out there, they're just carrying energy from one location to another. What's a power plant doing? Converting energy from one form to another, such that they can then transport it to you, so you in turn can convert that energy to another type. All of society is just changing energy from one type to another, which is kind of a crazy idea. That is what we do, and we're always increasing entropy, but decreasing in some local setting, whatever. It's a cool thing, and so this is why energy is so important for you all to understand, because at the end of the day, every single action is about changing energy from one form to another. When you're thinking, you're changing chemical energy to electrical energy and neurons and things like that in your brain, and then doing stuff with it, and great. It's cool. So, all right, that's two charges. This next slide is going to look all sorts of crazy, but we're going to apply it, and it's going to make a bit more sense. All right, so if I have more than two charges, if I want to find the energy of a system, how do I do it? First, I find the energy of one charge. What's the energy of one charge? Absolutely nothing. Because can one charge do anything to itself? No. There's no energy stored in that. How do I know that? Because it does absolutely nothing. It's not going to move. You let it go, it's just going to exist. How do you add energy? You bring in another charge. You bring in another charge, and you find how much you had to fight to make that happen. And that's how much energy you've added to the system. If you bring a third charge in, it is having to fight both of these. So the energy of a system is the energy required to bring a charge in, then another charge, then another charge, then another charge, then another charge, until you've built up all the charges in the system.
But what about that equation we went through in the last one? With like the one charge.
So that's if there's an external electric field, which could be, and again, that's a great point. If you had 100 charges to bring that last charge in, it had to fight the electric field due to all 99 other charges. So, this equation is going to look crazy. We're not actually going to use this equation in this form. At least I'm not going to. I'm going to teach you all kind of how to build it. But it kind of shows it. Every time you add a charge, so again, I'm not actually going to use this equation in its form. I'm going to show you all how I kind of work through it. But this is kind of the formal way of writing it. You find the energy required to keep adding charges. And it gets harder and harder to add charges to a system. Just like when you all blow up a balloon. Or blowing up like an empty thing. At first it's easy, and as time goes on, you're fighting the pressure inside that tire to add more and more air molecules. The same is true of charge. Every time you add a charge, you're fighting all the other charges. So when we talk about capacitors, it gets harder and harder to fill a capacitor. Your all's phone is another great example of this. Your all's phone charges real quick when it's at 0% because there's no charges you're fighting against. As time goes on, more and more charges build up on your battery that you're having to fight against. And that's why charging slows down as you get closer to 100%. It's harder and harder to add energy the more and more stuff you're fighting against. All right. So, I'm going to have you all think about this. If I have two charges, both positive, what happens to the net potential energy by bringing a third charge? And so here's my reminder to you all. The energy due to just two charges. But if I bring in the third charge, what's going to happen to my energy in the system? Will my new energy be 2 times this original? 3 times the original? The same or quadruple?
What happened to the negative?
The negative canceled out a while back. Yeah. And the integral, we got a negative because it was the 1 over r squared, and that canceled out the negative for us. Yeah. Just r. R is the distance between them. Oh, yeah. Thank you. I thought you meant the picture. Yes, correct. R. Be careful. It's very easy to accidentally add squares or not add squares when you're solving problems. All right, give y'all 20 more seconds. All right, we'll close it out in 5, 4, 3, 2, 1. All right, so here's how we're going to do this. We're going to build this system. So, how much energy does it, and we're going to build it one charge at a time. So how much work is required to make this one charge move there? 0. So the energy required to move the one charge there is going to be 0. The energy to move the second charge there, now we're having to fight. We're actually having to fight the other charge to make this happen. So this is the equation I gave you all that time. Q1, Q2 over R squared. Charge 1, charge 2. Awesome. That's the energy required to bring the second charge in. Yeah, thank you. Yeah. Don't fall into that trap. It's going to happen to you too at some point. To bring the third charge in, it has to fight both of the other ones. To bring the third charge in, I need to fight charge 1. So that's going to be Q1, Q3 over R. Plus, I need to fight charge 2. If I want the total energy, I add up the energy to build the whole system. To get the total energy, I'm going to add U1 plus U2 plus U3. And so I got 3 of them. They all have the same Q. So we end up with the energy of this system is 3 times bigger than the original. Adding a 4th charge would be a little funky because it'd have to form a tetrahedron and things wouldn't be like, it's a little tricky to do that. But there you go. Next class we'll talk about voltage. We haven't even seen the word voltage yet. It'll show up next class. Have a good one.
Thank you.
Yep, have a good one.